Hi, and welcome to our new chapter on Bayesian optimization. Here in this first part, we'll take a look at the larger picture of Bayesian optimization. I'll try to motivate the method before we start with the technical details. So, why are we actually interested in Bayesian optimization? Why has this become one of the most fundamental methods in AutoML and especially for hyperparameter optimization? So many optimization problems that we face in AutoML, especially hyperparameter optimization, but also to a certain extent neural architecture search, share three very common features. So the objective function is usually a black box, not always, but quite often. So that means, by that we mean it has no analytic form, and it's usually not possible for us to compute gradients. There are exceptions, but if we do a general AutoML approach where we optimize over different model classes, usually this is true. And usually the evaluation of this black box is expensive. So we have to either train a single ML model or we have to potentially completely resample this. So there are multiple training and prediction steps involved. And this can take somewhere between minutes, hours, or days. And the third aspect of this optimization problem is that it's often noisy, because the training can be stochastic. The data is random anyhow, so we should actually treat this output that we get from the evaluation of our cost function as a random variable. And taken together, these three characteristics imply that classic optimization methods, something based on gradients, maybe even evolutionary algorithms, which are good black box optimizers, don't fit here very well, especially due to this expensiveness of the evaluation. So we are interested in special techniques that can handle such problems, natively very efficiently, and Bayesian optimization is exactly that. Is exactly that. So let's take a closer look at hyperparameter optimization as an expensive black box optimization problem. So what are we actually interested in? So this was defined in a previous chapter already in this lecture here. So we want to optimize such a cost function here, and this cost function is simply our resampled performance metric for a given inducing learning algorithm with a given configuration vector lambda. Where our learning algorithm is trained on a training set and it's validated on a validation set. And I've simplified the notation here a little bit so it doesn't get overcomplicated. For a simple training and validation step, in general, we might use a full cross-validation here to compute this C of lambda guy. And you should now be able to see that this quite obviously has no closed form expression usually. This is more like a computer program that we can run and evaluate. The evaluation is usually quite expensive because of this training and prediction step. And we'll discuss this later more in detail, our hyperparameter space is often of a mixed or even of a hierarchical structure. So there can be numerical parameters in there. There can be integer hyperparameters in there, categorical hyperparameters, but even conditional hyperparameters, especially if we are configuring something like full machine learning pipelines. So let's maybe go a little bit through alternatives. This was also already discussed here in the lecture in the basic hyperparameter optimization chapter. Why would we usually not resort to manual tuning in HPO? So this would rely on expert intuition. This is not necessarily a bad thing, but I would say machines are like a little bit better on such problems than even an expert human modeler. I guess it's debatable. It is certainly, at least to me, quite annoying to do something like this manually. I do want to bring in my expert knowledge into a modeling problem, but not necessarily as, an optimization algorithm, so to speak. I more enjoy, for this part, automated procedures. If humans do this is usually poorly reproducible because people try stuff out, and then you have to somehow document this. You have to also somehow document, your workflow to reach your supposed optimum at the end. So this is usually poorly reproducible and it's hard to document and communicate this process. And it can also be prone to bias. So humans, they have sometimes they have a lot of, internal knowledge, but usually this also is prone to, a certain bias, certain familiar settings you have tried out, things you are more familiar with due to, I don't know, due to education, and you might miss interesting regions in the search space, in the configuration space. And for all of these reasons, we, or I guess at least as the AutoML community, and I specifically, I like systematic, adaptive, and reproducible alternatives for this. Why are we not using simple techniques like grid search or random search? They have also been introduced before already. They have a lot of advantages, so they are simple and parallelizable, but they are non-adaptive. So every configuration is sampled independently of its previous results. There is no exploitation of structure of our objective function. Budget is usually wasted on obviously unpromising regions, and hence this scales quite poorly in higher dimensional configuration spaces. And especially if your objective is expensive, especially if you're working in higher dimensional configuration spaces, usually would like an optimizer that learns from past evaluations and that follows promising local directions towards more interesting regions in the configuration space. So in order to visualize that, I have used the Branin function here as a test case. You can see how random search distributes points. You can also see where the local optima of the Branin function are here down below, and you can see that we are, missing them by quite a far margin, but this is very, natural or obvious. I'm just putting a few random points into the configuration space. For Bayesian optimization, which I've already run here, you can see that points cluster in a much nicer fashion around these optimal regions. And of course, some points are also used for exploring the search space, and this trade-off between exploration and exploitation is exactly what I'm going to talk about much more in the upcoming slides. And you can also see here that this, of course, then gives rise to better optimization performance. Okay, maybe a few words about full machine learning pipelines. So these can nicely also be configured by Bayesian optimization. So in that instance, we would have our configuration vector lambda here encode all pipeline choices. So not just the hyperparameters of a single learning algorithm, but all of the hyperparameters of the complete pipeline, potentially even including different, operation choices. So maybe there's some imputation for missing data going on. Maybe there's some scaling going on. Maybe some feature selection. Maybe we would even have different machine learning algorithms at our disposal. And all of these, choices that we would have to make for the pipeline, we can encode in our lambda vector. Our C of lambda is again simply our resampled performance for the complete pipeline. So there nothing really changes. And structurally, our optimization problem also hasn't changed that much. It's pretty much the same problem we are facing with the same properties. The only thing that has potentially changed is that our configuration space is now likely higher dimensional, because there's usually more choices in there when we are configuring such a complete pipeline. And it's also potentially more of this mixed and hierarchical structure. What is the core idea now of Bayesian optimization? I'm not going to talk about this too much here in this first part, but let's do a short introduction to the technique. So the core idea is to fit a cheap surrogate model, and I'll call that C hat, in order to make clear that this is estimated on data, on observations that we've collected during the optimization. And we will use this surrogate now to form a so-called acquisition function. And this acquisition function is supposed to trade off exploitation versus exploration. So exploitation would mean that our acquisition function is supposed to be high when our model or surrogate model predicts good values to be at that place. And it's also supposed to be high when our surrogate model is uncertain. So usually our surrogate model is going to be uncertain when it hasn't seen lots of experiments near that, queried point, near that point under consideration. And at the end, we want to have an acquisition function that trades off or that incorporates both of these aspects quite nicely. And then what we will do is we will evaluate our true objective only at the most promising point according to this acquisition function. So this will be the one expensive evaluation we will do in one iteration of Bayesian optimization. Then we will update our surrogate based on our experimental results, and we will repeat this in a loop. And all of these details will become much clearer in the upcoming subchapters. So at the end, what we want to produce is a sequential, model-based, sample-efficient procedure. And this is exactly what we would like to have for a setting where each evaluation in such an expensive black box scenario is very valuable. We want to exploit and use as much information from the past evaluations, from the current optimization trace as much as possible. BO really has become a backbone of many modern AutoML systems. Tools like SMAC, BoTorch, and Aptuna. And it's typically way more sample efficient than random search or evolutionary search on HPO benchmarks. And it also, and that's also quite nice, usually gives us a principled way to handle things like noisy evaluations, multi-objective optimization problems when we want to incorporate things like, runtime, fairness, interpretability. There are multi-fidelity variations of Bayesian optimization, warm starting procedures, mechanisms to incorporate priors, and so on. I'm not going to talk about this more in this chapter here, but many of these aspects we will explore in later and more advanced chapters on AutoML. What is also interesting to note is that this same expensive, noisy black box setting that we see in the definition of our hyperparameter optimization objective function in AutoML, that this setting also appears in quite many other parts of science or computational science. So I've started out here with two, individual examples. So maybe we want to optimize a parameterized controller of a robot so that the robot walks fast and stably. And this is certainly an expensive problem. Usually this is black box, so we can only observe, the performance of the robot under this parameterized controller. And we will not be able to run too many experiments. There's also a fun little paper where they're using Bayesian optimization for baking cookies. So maybe we want to find the ingredient ratios that maximize the taste, or a quality rating. So that's not even a computer experiment, that's a real-world experiment, and you can use Bayesian optimization for that as well. But more seriously, if you look into very many, areas of science and engineering, drug or material design, chip layout optimization, physical experiments, very often things you can somehow simulate in a computer. You want to optimize certain settings there, and you can measure performance. And this is very often expensive, noisy, and black box. And very often Bayesian optimization or related techniques are used for optimizing such scenarios. And this also is, as tightly connected with the historical roots. So of Bayesian optimization. So Bayesian optimization actually didn't really, original in ML, or let's say for AutoML. It grew out of an area which was called design and analysis of computer experiments. You can see here a very famous book by that's from the end of the 80s. So in the classical engineering setting where these techniques were applied was, some optimizing a run of, a physics or a CFD simulation or finite element simulator that could take up to hours or days. And the idea was to treat the simulator as an unknown function, fit a Gaussian process, sometimes also called kriging, to a small design, and then use this as a cheap proxy and optimize this. And then there was this very seminal paper by Jones from the end of the 90s, who didn't really invent Bayesian optimization, but who popularized this under the name of EGO, for efficient global optimization. And that specifically pairs a Gaussian process with the expected improvement acquisition function. And this is exactly what we will talk about in the subsequent parts of this chapter here. And this is directly the ancestor of today's Bayesian optimization. Actually, it's its most popular variant. Quick summary and an overview of the guiding questions for this chapter here. So we will talk about how does the basic Bayesian optimization loop look like? How do we quantify uncertainty with a specific surrogate model? How do the most common acquisition functions look like? How do they balance exploration and exploitation? And how do common surrogate models work? So we'll take a look at Gaussian processes and also at random processes, my God, random forests, and especially their uncertainty estimation, because this is not completely obvious for that model class. And we'll also discuss a few slightly more advanced choices, variants of Bayesian optimization that matter in practice. So especially how do we optimize the acquisition function and how can we create parallel versions of Bayesian optimization.